Okay, this is session number 6 out of 10 or 11 as the case may be. We're still planning that. I have a cold, a possession I am not proud of, but it's going to be immortalized on video now. Every squawk, every cough. You may be able to edit out some of the coughs on the video, I don't know. Tonight's topic is, what is mathematics and can we trust it? And the questions I raised this time are going to involve some things you've probably never thought about, didn't even know that they were questions, and yet they've been a major concern of many important thinkers for a couple of centuries. But before we do that, I want to interject a few thoughts about where we are and what an odd thing it is to have a history of science course in a church and where we are as a result of that. I hope that many of you are feeling relieved, as one person said, that said to me that we are not expected to think like people with considerably less education. We're allowed to use our education and relate it to our spiritual life. For decades, much Christian education and church activity have been out of step with the actual educational level of the congregations, particularly if they're not Presbyterians. But different denominations have approached this differently, and some have done better than others. But there are really 3 things we need to mention that keep Christians separate from science. One, which we've dealt with at great length already, is the notion that science is somehow inherently ungodly, atheistic. Science is what you have if you don't have God. Science is the opposite and should be avoided by godly people. There is what I just mentioned, a tradition probably going back to our forebears out on the frontier with nothing but their Bibles, of not expecting a lot of education among Protestant churchgoers, particularly in rural areas, and that is practical. If you read your Bible a lot, you can learn a lot, and you can come to a very subtle understanding of a lot of important issues, even without higher education. What you can't do is relate to the things that the highly educated people know about and think about. And that's an essential thing we need to do, particularly if we are the highly educated people, as we are now. The third thing is, and I didn't mention this before, didn't think of it, our academic culture has a split between the arts and humanities on one side and the sciences on the other. There's the expectation that a person cannot be good at both, and that if you're in one, you have a right to ignore the other, and that religion belongs in the humanities side. So an English major might know something about the Bible, a chemistry major need not at all. The English major probably needs to, in order to understand literature, whether or not they are a believer. They need to know what's there. So if you make a sharp split between sciences and humanities, you end up cutting people genuinely interested in God off from people who are genuinely interested in science. Theologians tend to be undereducated about science, except when they're not, and T.F. Torrance is the example that comes to mind. Any of you ever read anything by T.F. Torrance? I thought, perhaps mistakenly, that he is he still with us? Greatest living Presbyterian theologian, I thought, over in Britain in the Church of Scotland. I heard him lecture at Cambridge. That is the lecture at which one of my friends squealed with intellectual delight. I had never heard a girl squeal with intellectual delight before. I told you about that, didn't I, Melody? But yes, T.F. Torrance, known for his very sophisticated and precise handling of the Trinity, among other things, uses science as a source of ideas for theology. I'm not absolutely sure he's still alive, but his career certainly spanned ours to a considerable extent. So if I can do one thing for Christian apologetics and Christian education and even evangelism, I want to convince people that science literacy is a good thing to have. Okay, I said this wasn't going to be a course on my opinions, so let's get to something that's not my opinion. I want to talk about the foundations of mathematics crisis, which is the most important episode in the history of science that you have never heard of. It's been a so-called crisis from the early 1800s or slightly earlier, the time of Gauss, to the present. And what is it? Well, the basic questions are, is mathematics reliable? Is all commonly accepted mathematics even true? Could there be things in your math books that will turn out to be wrong? Can you ever use methods that are described as correct in the math books to get a contradictory or false result? Why can we rely on mathematics? Well, obviously, anything that gives wrong answers to practical problems would be weeded out. But is there dirt lurking in the nooks and crannies? Special cases, do things work with really large numbers the way we think they do? Or something else unusual, really small numbers? An even deeper question, is mathematics something we discover by observation and reasoning, or is it something we invent the way people invented the game of chess? Could we invent a different variety of it? Imagine inventing a variety of chess that has one of the rules different, or inventing a variety of mathematics that has one of the rules different, and still get something that makes sense in some way. Obviously, you can change games and sometimes come up with a game that's interesting to play. Chess got massively simplified and we got checkers. Soccer got massively complicated and we got American football. To soccer add every complication you can think of, and there it is. The sport that has everything. But why is there even such a thing as mathematics? And why is it so useful for describing the world around us? These are questions people didn't even ask until about the time of Gauss, late 1800s. And related to that is, where do we put God in all of this? And the answers to some of the big questions are going to be different depending on whether you believe there is God, and God in his mind can understand things even if we don't understand them. That completely changes the question. Now, the classical view, rarely contested until the 1800s, is mathematics is something we discover by observing the physical world and by reasoning abstractly. Geometry is the study of the shapes of real objects. Abstracted, of course. That is, we're not caring what objects they are, and we're thinking about perfectly straight lines, perfectly flat planes, and so forth. But it's based on the study of real objects. Arithmetic is the study of the numbers and sizes of real objects, numbers and amounts. And this is what mathematics is. It tells us about the world around us. Copernicus, Galileo, Kepler, and Newton, our heroes from last week's session, felt that science improves by being mathematically better. So Copernicus's planetary system is better than Aristotle's or Ptolemy's physics because it's better mathematics. And the reason for moving on from Aristotle is that compared to them, Aristotle is mathematically illiterate. There's so much he doesn't know about mathematics. As Galileo put it, the book of nature is written by the hand of God in the language of mathematics. It was particularly Newton who made mathematics the key to all science, or tried to, and everybody followed in his footsteps. The classical view is that when we do mathematics, we are thinking God's thoughts, we're understanding things that the omniscient deity already understands because we're made in his image and likeness. We're doing something God does. And I think this is still the case, but there has been a crisis. There's been something to sow doubt about that. Cracks in the foundation of mathematics. Well, there are two foundational issues I want to talk about. There are several more that mathematicians know about. By the way, Christians are all over the place in the history of mathematics, and I regret that I haven't named them. Gauss, Cantor, and several others. Devout Christians just keep popping up in the field. But the two cracks in the foundation that I want to point out is Euclid's geometry all that it claims to be? That's a concern that's been smoldering since the Middle Ages, and it really came out into the open in the 1800s. Is Euclid's geometry as perfect as people claim? Is it totally consistent? Is all the logic perfectly correct in all of it? And the other is calculus, which we use all the time in the physical sciences, based on totally correct reasoning, or are there places in it where somebody just guessed and got a right answer but couldn't prove it? Does calculus rely on that kind of thinking that's heuristically correct and that it gets you to the right answer, but it doesn't actually have solid logic to justify the steps? It's more that you saw what the right answer needed to be and you just sort of jumped to it. Let's start with Euclid. You've all probably had a course in Euclidean geometry that is very much like what Euclid wrote in ancient Greece, because now they teach it in 10th grade, I believe, or they taught it to me as a 10th grade subject. It's almost exactly the same. High school geometry today. You have points and lines and angles. You have constructions with compass and straight edge. You have step-by-step proofs. And what do you do in a proof? Well, I'll get back to that, but Euclid's geometry for millennia has been considered to be the crown jewel of mathematics. It shows ordinary people, even high schoolers, just how much you can accomplish by reasoning logically from first principles. You're given a set of first principles, they're called the axioms and the postulates, and you're supposed to deduce all the rest of geometry from these. So when you do a proof, you can take any of the axioms and then deduce things from them. But did Euclid get it all entirely right? He had a system of axioms and postulates from which you were supposed to be able to deduce all of plane geometry. He had a lot of things deduced from it that were obviously right. But is all the logic perfectly solid between the one and the other? One of Euclid's postulates that made people uneasy is the parallel postulate. That says that in a situation like this, you have a line crossing two more lines. If the angles A and B add up to 180 degrees, then the first two lines are parallel. They never meet. Well, no one denies that that's correct. No one doubts that it is correct, but do you need it? People kept having the nagging suspicion that you could do all of geometry without that postulate. That's an unnecessary one. Well, how do we investigate this? Lots and lots of thought was expended on this, and the results, the conclusions were, no, you can't do without this postulate and still have Euclid's geometry come out right. It seems to be carrying very little load, but you do need it sometimes. And if you change it, here's what's strange. If you change it, you can still have geometry. It just isn't the same geometry. It need not be something massively self-contradictory or anything. It's just different non-Euclidean geometry. Non-Euclidean geometry uses alternatives to the parallel postulate so that in effect the plane acts like a curved surface, except it's still a plane. The angles of a triangle don't add up to 180 degrees. And the best known non-Euclidean system is that of Riemann, actually a large family of systems which in general have no parallel lines. That is, in most kinds of non-Euclidean geometry, there is no way to make a line that will never meet another line. Now, let me pause for an example here. In essence, in non-Euclidean geometry, the plane acts like it's curved. Let's think about geometry on a curved surface. Imagine a globe of the Earth. You know what latitude and longitude are. Well, at the North Pole, consider the lines of longitude, 0 and 90. One of them runs through London, one of them runs through Texas. They're 90 degrees apart at the North Pole. They both meet the equator, and each of them makes a right angle with the equator. So you have a triangle there made of great circles on a sphere whose angles are 90, 90, and 90. They add up to 270, not 180. I did that without drawing a picture. I hope you were able to follow it. On a sphere, there are no parallel lines. That is, there is no great circle where you can, a straight line on a sphere is a so-called great circle, something that would look perfectly straight as seen from the center of the sphere. There are no parallel lines. If you're thinking the parallels of latitude are parallel. Yes, but they're not lines. They're circles. Only the equator is the spherical equivalent of a straight line. All the others are circles. If you stand on the North Pole and look at some of the nearby ones, they're obviously circles running around you, not straight lines on the sphere. So if the plane acted like that, that would be one kind of non-Euclidean geometry. Turned out Einstein had a use for non-Euclidean geometry.
I wanted to add quickly, when the girls were in high school and encountering this for the first time, I used the globe in a piece of string to show them great circle paths from one location to the other. That helped them understand it.
We can no longer assume that Euclidean geometry describes physical objects. We actually now need to test and measure whether real objects in real space obey Euclid's system or something slightly different. We know that Euclid's system is very close to what we encounter in real life. We may never have found a discrepancy, but does it really have to be? Is it the only way geometry can be? No, it's not the only way geometry can be. It could be slightly off from that, and we might want to sniff around for evidence whether it is. Okay, I now want to talk about the other crack in the foundation, calculus. How many of you have had a calculus course? Okay. The question arose whether calculus is solidly logical or if it has guesswork in it. Now, I need to tell you what calculus is about for those of you who may not have it all fresh in your mind. I'm glad so many of you do, by the way. It's the study, basically, of instantaneous rates of change. What do I mean by that? I'm now going to do something that is a classic part of college teaching. I'm going to wave my hands. I'm going to teach by waving my hands. So what I'm about to tell you is not on the slide. Imagine an object moving at a constant speed, maybe 1 foot per second. What do you mean by 1 foot per second? Well, in 1 second it moves a foot. Equivalently, in 1/10 of a second it moves 1/10 of a foot. In 1/millionth of a second it moves 1/millionth of a foot. Okay, distance divided by time is the speed. Okay, in 0 time, how far does it move? It doesn't move in 0 time, right? All motion takes time. Now, imagine an object moving and changing its speed, like maybe slowing down to make a soft landing, or speeding up the way things do when gravity is pulling on them or something. What is its speed when it's right here? How could you answer that question? Well, the first thing you might think of is measure the distance and time for a small part of its path that's close to here. And if you have a distance and a time, you have a speed. But I didn't ask what's its average speed over this much of its journey. I asked what's its instantaneous speed right here. Do you want to say it doesn't have a speed for a 0 length interval? It still has a speed. It's obviously still moving very much like the way it was moving above and below that point, just a little bit different. That is the concept of a derivative in calculus, an instantaneous value of a changing quantity, or potentially changing. Now, here's the logic problem. Pardon the change of type font to make this legible. When you took calculus, you saw formulas like this. Speed is the amount of position change divided by the amount of time that went by. Delta there means change, so change of x divided by change of t. Well, in calculus, we would write the instantaneous speed this way, dx over dt, where d means change over a zero length time, change over zero length, something like that. What it exactly means is the problem. Okay, the problem is what this means because it looks like you're dividing, and it obeys a lot of the laws of algebra as if it were a division, and yet you're dividing by zero because I talked about over no distance at all. Now, what is going on there? As recently as 100 years ago, I started to learn calculus out of a really obsolete book more than half a century ago, and that book was actually that old. They did seem to think it was a division. But if so, it's a division by zero. So as recently as before World War II, some calculus books treated dx and dt as if they were numbers that you could divide. But they were supposed to be infinitely small numbers. Now, what's the difference between an infinitely small number and zero? That's the problem. If that seems not to quite make sense, you're right. It doesn't quite make sense.
This is where calculus was really hard for me.
I'll bet you were taught a slightly out-of-date approach because...
I learned from a workbook. My teacher couldn't deal with calculus either.
Ah, okay. This is when Winterboro High School was running out of courses to teach you?
Yes.
Yes. She exhausted a whole high school. But it seems that calculus works, but it's full of invalid divisions by zero, and in integrals, multiplications of finite quantities by infinity giving a finite result, which isn't right, and yet it works. It gave Newton the orbits of the planets, it gave everybody else the correct solutions to a huge number of physics and engineering problems. So we had a branch of mathematics that seemed to be built on very shaky ground that didn't intuitively make sense. And the smarter students, like Melody, realized it didn't intuitively make sense at that point. Others just learned to play the game the way the game is played. Calculus is now understood as based on the concept of limits, of the lower or upper bounds of sets of values. So the idea there is, if you're asking the speed of my hand right here, well, it's approximately the speed as it traverses this. More accurately, it's the speed as it traverses this. More accurately, it's the speed as it traverses this and this and this and this and this. And we never actually measure it moving in zero time, but we show that as we shorten the time interval, the values get closer and closer to something. That's the theory of limits. And alternatively, there's this eccentric fellow named Abraham Robinson who made up a system of arithmetic. You know, there's non-Euclidean geometry, there's non-standard arithmetic, in which these infinitely small numbers really are numbers that you can do arithmetic on, as if there were numbers between zero and the smallest real number, whatever that might mean. Basically, I think he picked up the theory of limits and moved it into the number system. Anyhow, that's a sample of the foundations of mathematics crisis, and that headache you had on the first day of calculus was perfectly justified. You had bumped into a major philosophical problem.
So I know we do questions at the end. Can I ask a quick one?
Certainly.
So what's taught today?
Theory of limits.
Okay.
Definitely.
So there is, that's the old calculus, theory of limits?
Well,
That's the new one?
that's everybody since the mid-1800s who was really on the ball. Robinson's non-standard is not taught much of anywhere except by David Billington in Australia. He introduced me to it. It's not the usual approach.
So really quickly, would a teacher, would Mary teach calculus and say, now in this particular instance, there's this guy named Robinson who might, or would they like, is
No.
it up to the teacher, just kind of let that go and not worry?
You can leave Robinson completely out. The theory of limits due to Cauchy and others is universally accepted, and the very few that do like Robinson's approach agree that it's equivalent to the theory of limits. So Robinson is an outlier, a peculiarity there. Where do we go from here now that we've had our faith in mathematics so badly shaken? The game has changed. We now see mathematics as something that we're making up, rather the way people made up the game of chess. We can make up different versions of it and see how they turn out. Except, when you make up a game, you still have to play it by its rules to find out how it's going to come out, don't you? So in that sense, we have to discover what follows logically from whatever we started with. It's as if logic is still fixed rules. There's also debate about the foundations of logic. That would be another talk. I actually know more about that than about the foundations of mathematics by quite a bit, but I won't bore you with it. So in that sense, mathematics is still discovered and is rather like making up a computer program and then running it to see what it does, see what it actually does. You make up a system of non-Euclidean geometry and then run it according to its own rules to see, what the angles of a triangle add up to in it and what other peculiarities it might have, how you would measure a difference between it and Euclidean over a particular size space and so forth. We can no longer assume, and this is what really upset people, we can no longer assume that mathematics is built on a foundation that is perfectly clear and which we understand perfectly. It never was. Mathematics is a collection of things that we know work well, we can use them to solve real-world problems, built on foundations that we may or may not understand. We no longer have perfect certainty. We cannot even assume that all of mathematics as we know it is correct. There were incorrect things in calculus books 100 years ago that simply do not give you the right results under all circumstances. So when we do mathematics, are we still seeing the mind of God? Or do we have to throw that idea out?
I would place money, even though I'm not a betting person, I would place money on the idea that we haven't discovered all of the things that we need to understand the mind of God.
Given that God is infinite, that seems sort of obvious, doesn't it?
Yeah.
I think God knows Euclidean geometry and all the non-Euclidean systems that are possible. And also the ones that don't work and knows why they don't work. And also where all the bugs are in Windows 11. That's divine omniscience, right? The next 3 slides are going to be my considered opinion, not the consensus of all scholars or historians. There do get to be some of my opinions in the latter parts of tonight's talk. And I said this was not a course on my opinions, so let me give you some truth in labeling here. Some philosophers have despairingly or gleefully concluded that all human knowledge is fundamentally uncertain. You can't even trust mathematics. That proves there's no absolute truth, nothing to be known, just think whatever you want to think. I am not one of those philosophers. We already knew we were fallible, didn't we? Even if mathematics had been as perfect as we thought, we were always at risk of making mistakes. That is, not following the rules properly, especially when they get complicated. We already knew that our knowledge was incomplete. And this doesn't mean that there's no absolute truth, only that our grasp of it is limited. If you believe in God, that's where you should have always known you were. But if you believe that human brains are the only intellects in the universe, this is definitely disturbing, isn't it? There's no absolute mathematics, there's only what goes on in human minds, no mind of God. You see the difference between the theistic and non-theistic positions, and this is why I think atheism is not merely one big problem, it's an infinite number of big problems. And I will keep God right where Copernicus, Kepler, Galileo, and Newton put him. Now, does any of this have anything to do with what you have heard of as new math in the schools? You know far more than I do about this, but allow me to rant just a little about the ignorant things I hear people say about new math. Is the foundations of mathematics crisis the new math we've been hearing about in school? Not really. although an interest in the foundations of mathematics did lead to a new interest in teaching methods, it may have spawned the very subject of mathematics education, because people started thinking deeply about what is it we're learning here. One thing that saddens me about American culture is how many people brag about being bad at math. Nobody brags about being bad at driving a car, though you can see they are. And some people object to almost any method of teaching mathematics. I feel that mathematics is the extension of common sense by other means, as Jordan Ellenberg put it. But I will be the first to admit that if it's taught badly, it can be agonizing. There are two subjects that a bad teacher can make extremely hard without doing extra work. You know, in most subjects, to teach a hard course is more work than teaching an easy course. But there are two subjects where a bad teacher, without doing extra work, can make it extremely hard. They are physical education and mathematics, in my opinion. So there are actually two things that seem to go by the name of new math. And do correct me if I'm off track here, but it originally meant a move to teach a more abstract kind of mathematics in elementary school in the 60s and 70s. And nowadays, I think it means a variety of newer methods to try to get people to understand numbers as amounts, not just as figures. And what I'm saying in the next couple of slides is based on my own experience trying to communicate with non-specialists about mathematical things. You run into all kinds. Also reading people on Facebook ranting about the way math is taught. Can't stand those number lines, they're nonsense. No. New math in the first sense it's actually something I fell right into the middle of. Second grade, Moultrie, Georgia, a really, really good teacher named Myrtle Lofton. If anybody else who knew her ever sees this video on YouTube, please let me know. The idea is you teach concepts like sets and greater than and less than and so forth, not just fiddling with numbers in pencil and paper and getting the answer, but instead, what do these numbers mean? How do they relate to other numbers? I thrived on it. I was in my element there. Many teachers apparently didn't teach it well, and it wasn't generally considered a success. I'm not totally sure it was given a fair trial, but it's in any case not what's going on now, but some of it did endure. Nowadays, when you come across new methods, the basic context is this. We have calculators to do the number crunching. The people need to know why they are supposed to be crunching numbers and whether the answer looks right. Okay, you can't get a job today doing pencil and paper arithmetic all day long. A certain episode of the Beverly Hillbillies may come to mind, Jethro and his ciphering. But the point is, you can't get a job today doing pencil and paper arithmetic all day long. You also can't get a job today handwriting things in cursive all day long. That's the other thing people rant about, that cursive handwriting is dying. I think that in 1965, they should have been teaching me to type rather than all those hours of Zehner-Bloser method cursive designed for dip pens that had not been used for 150 years at the time. But anyway, getting back to this, I have encountered people for whom all numbers are like telephone numbers. That is, there are people to whom a number is not really an amount. It's just figures you write down. And you learn procedures called addition and subtraction and multiplication and division that you can do on these meaningless strings of digits, and you may be quite proud of how well you can do these procedures and get another number out. But there are people who, in spite of being good at that, do not see numbers as amounts and are not good at estimating them or putting them to practical use. And the way we shake people out of that particular limitation, well, these would be the people who don't see that obviously $19.75 is a lot closer to $20 than to $19. Or they would only see it by imagining the dollar bills and the quarters. It's funny how in the really old days, counting money was almost a separate thing from arithmetic. And somehow counting money was real when arithmetic wasn't to some people. Or that if you multiply 4 times 20 and get 8, you're way off, right? You've punched the wrong buttons on your calculator. So I actually gave a math readiness test once at the beginning of a computer programming course, and as the easy throwaway question, the question was, what is 25% of 60? I got 1,500 from one student. And then what? No, 25% of 60 is going to be less than 60. That's the way a person who is aware of numbers as amounts would start approaching it. So the correct answer was 15. If I'd gotten 25, I would have said, well, I know what you did, but it's at least plausible. 1,500 is not. People who are not good at pencil and paper arithmetic often think they are no good at mathematics and will never enjoy it. That was almost me for a while. The way I sum it up to people is arithmetic tells you how to add 124 plus 659. Mathematics tells you why to add 124 and 659. Arithmetic is now done by calculators, but you need to be able to see if the answer looks obviously wrong. Nowadays, we're likely to make big mistakes, not small ones, if we hit the wrong buttons on the calculator. Now, a very important new skill that is emphasized finally, because everybody who really used numbers always did a lot of this, estimation. Now, the weirdest thing I have heard, some type of critic of modern education said, well, estimation is this postmodernist liberal notion that math problems don't have real answers, just estimates. No, estimation is based on the idea that they have exact answers and you want to be able to get close to them even sooner than you can get to the exact value. So there's nothing postmodernist or relativist about teaching estimation. It's something that everybody who actually uses numbers does all the time. Number lines. I see parents on Facebook ranting about these nonsensical number lines. Their purpose is to teach you to appreciate numbers as amounts and distances. If number lines mystify you, I say to people who are ranting against them, can you use a tape measure? Ever used a tape measure? What do you make of a tape measure if a number line mystifies you? It's the same thing. Okay, end of rant there. I do need to deal with one more thing. To deal with a lame joke that's been going for 60 years and needs to die. There has never been a new math taught in school in which 2 plus 2 does not make 4. Or anything like that. And I mean, everybody agrees about the facts of mathematics. And in fact, in Robinson's non-standard arithmetic, even there, all the calculations with real numbers come out exactly the same as in standard arithmetic. He just has this change of rules so you can divide dx over dt in his system. So, pardon me for going off topic. I figured you'd ask me about new math if I didn't say anything explicit. Next time, we're going to have 2 sessions on biology, each involving both Chapter 5 and Chapter 10, and we're going to have a guest speaker, my daughter Sharon Covington, the Emory-trained biologist and possible stand-up comedian. Well, maybe not quite, but she's a very entertaining speaker.